Okay, I think we are ready to start the afternoon session now. And the first talk is given by Serena DeBeer. She's an expert in X-ray spectroscopy, and that is the official beginning with our tour through the electromagnetic spectrum and to see what it all can do to for bioinorganic chemistry for us. Serena, thanks for coming.
Yeah, thank you, Karsten, for the introduction. And I guess before I even start, I really want to thank all of the Penn State crew, and especially Karsten, for putting together this program and for the opportunity to participate in this workshop again. So as Karsten told you, today I'm going to tell you about X-ray spectroscopy. I'm going to primarily focus on X-ray absorption spectroscopy, which is probably the better-known method, particularly in bioinorganic spectroscopy. And then towards the end of my talk, I'll talk a little bit about X-ray emission spectroscopy, which is an area that's particularly close to my heart and that my group has had a lot of activity in the last few years. So basically, over the next several days, you'll basically be taking a journey through the different spectroscopic methods that have been really important in bioinorganic chemistry. And I think this is one of the really great parts of being a bioinorganic chemist, because this is a community that embraces such a wide variety of methods and really combines those methods in order to get detailed understanding. And I know sort of you've seen the same slide in Frank Nase's talk, and this is sort of kind of a view of the bioinorganic chemist's toolbox. It's a pretty big toolbox. It's pretty varied. And it basically uses the idea that if we use light of different energies and interact it with matter at each area of the electromagnetic spectrum, we get different and complementary information to ultimately build up a detailed picture. Now, for me, having sort of grown up in Ed Solomon's camp of bioinorganic chemistry, of course, it's quite necessary that any slide always had a minimum number of spectra, at least this on any given slide. But I'll point out to you that actually so many of your speakers actually came from the same camp, including Frank Nase from this morning, Nikolai Leonard, who will speak later, Dean Wilcox. And with that, I really should point out to Frank Nase the number of people he insulted when he said that the MCD spectra he showed were in fact ancient, because those were spectra from my own PhD, and I'll remind him from his postdoc. But with that said, certain things remain classics, and we're going to sort of be taking you through a journey of some of those classic applications in bioinorganic chemistry. And today we're going to focus on the high energy side of the electromagnetic spectrum and the kind of information we can get by using X-rays. So for those of you who have some familiarity with X-ray spectroscopy, you're probably well aware of the fact that most of the time we need very intense sources of X-rays to do this kind of spectroscopy. So that means the majority of what you see in the literature was done at a synchrotron source. What happens at synchrotron sources is basically electrons are accelerated to relativistic speeds, and in doing so, one produces very intense sources of radiation. This is a plot of the photon energy one can achieve versus spectral brightness. Now, by spectral brightness, what I mean effectively is the concentration of X-rays that you can get out of these sources. They're very concentrated sources of X-rays, so to put that into perspective, if you look at standard laboratory fixed anode sources, they would be down here producing something at maximum of peak spectral brightness of about 10 to the 10th. If you look at third-generation sources like SSRL or NSLS, these are synchrotrons at Stanford and at Brookhaven, they're up around 10 to the 12th, whereas some of the new generation sources in free electron lasers, they're about 1 billion times brighter than what you can produce in a lab. And so these are really amazing sources to do a lot of interesting types of core spectroscopy. This actually is also a very fun field to work in. So this is, I guess, a plug and advertisement for my own group, because there's only about 60 synchrotron facilities worldwide. Each of those facilities can be unique. They can offer the ability to do different types of experiments. And so it also means that you might have the opportunity to travel to do these kinds of specialized experiments. This is actually a map of where my group has been doing experiments around the world in the last couple years. since we moved to Mulheim. And for those of you who eventually will meet your tutors, Nicole Verster and Stefan Hugenbrook, they just returned from our group's first beam time in Brazil. So there's lots of fun opportunities. But it sounds kind of fun, but you sort of have to be honest. If you ask them, the reality is when we have beam time, we don't actually really sleep very much, or at all. And you work very intensely 24 hours a day to use these really sort of limited resources. And so you might be thinking, why do I care about X-ray spectroscopy? I have no desire to ever be one of these strange people who spend sleepless nights at a synchrotron. And the good news is even that is starting to change. And so in my view, when you think about X-ray spectroscopy, you also need to understand it's at a turning point. I think in many ways it's where NMR was maybe 20 years ago. What we're starting to see now from, in fact, multiple companies in the world are some of the first tabletop synchrotrons. So the first one was actually produced by Lincian Technologies, a company in Palo Alto, California. It has a $10 million price tag, so probably not the average instrument that everyone's going to buy. But there are other possibilities one can think about. So what I talk about today, and when you think about what kinds of things could I do with X-ray spectroscopy, my group and I actually recently received funding from the European Research Council. We're building up our first in-house setup to do dispersive X-ray emission. It's a collaboration with Birgit Kangieser's group at TU Berlin. But the idea is when I get to the time, to the emission measurements at the end of my talk, realize that at least we hope by the end of December 2015 to have our first in-house setup. So these are real things that you hopefully can think about in your own careers, that really you don't necessarily have to do this at a synchrotron. And if you are a real synchrotron jock or you really like the idea of free electron lasers, there's also possibilities for all of the methods I've talked about to really be pushed forward in the time domain. That's happening at places like the LCLS at Stanford and at the free electron laser in Hamburg, where people are doing things like femtosecond crystallography, femtosecond X-ray emission, and all of this is sort of happening, and it's kind of exciting opportunities. So now let's get to really the meat of my talk and go into some of the more basics instead of what could happen in the future. So what I'd like to do today is to first begin by giving you a general introduction to X-ray absorption spectroscopy. So we'll start by talking about the X-ray absorption edge region, or what is often also referred to as the Zanes region. This stands for X-ray absorption near edge structure. We'll go through just some basic definitions of what this is. We'll look a little bit at the experiment, what you can get out of it, and talk about how you analyze this. We'll then go also through the X-house region, and then towards the end of the talk about X-ray emission, and time permitting, we'll go through some applications of these methods that combine different types of X-ray spectroscopy. Okay, so let's just start with the very basics. When we talk about an X-ray absorption edge, that edge results whenever a core electron absorbs an energy that's equal or greater to its binding energy. So if we basically bring in enough energy to excite, for instance, a 1s electron of copper, a copper K-edge results. At lower energy are excitations from the 2s and 2p shells. These are referred to as the L edges. They take about an order of magnitude less energy. And then from the 3s, 3p, and 3d shells, these would be the M edges. Now, what's important to note is I'm showing you the values here for copper. If I instead wanted to do X-ray absorption spectroscopy from, say, iron, you can see that the energies are very different because the energies, of course, of the core electrons of iron and copper are quite different. This is important because fundamentally it makes X-ray absorption spectroscopy an element-specific technique. So for whatever enzyme system you might be studying, whether it contains calcium or it contains zinc or anything in between, basically if we can access the energy, we can do a core excitation and selectively look at that element. And that's one of the really great strengths of any kind of X-ray core spectroscopy, including the emission methods. So let's just first talk about the basic spectral regions. In general, when we talk about X-ray absorption spectroscopy, we divide the spectra into two separate regions. This is what we already talked about, what's often referred to the pre-edge and edge region. So in the edge, This is where you see the sharp discontinuity that results from the absorption of that core electron. Okay? And this particular region provides us with electronic information about the absorber, as well as local geometric information. Now, after that photoelectron has actually been now ejected to the continuum and it can interact with its surroundings, what we get is a very weak fine structure known as the extended X-ray absorption fine structure, and that can provide local metrical information around an absorbing atom. And we're going to talk about that more in detail, about exactly how one goes about extracting these different pieces of information. Okay, but for now, let's first focus on the first part, which is the edge region. And let's talk a little bit about why one might be interested in actually getting an X-ray absorption edge. As I've already said, X-ray absorption is element-specific, and it can be applied to almost any system. So basically, samples of any form, at any temperature. And so it basically is very versatile in that sense. In terms of the kind of information that one can get out, it's sensitive to both geometric and electronic structure of the absorber. So this means that we can get information out about the oxidation state of the absorber, the spin state, the ligation, and the site symmetry. One of the things, though, that perhaps isn't surprising when you think about these intense sources of X-rays is they can also cause damage. This is something that you'll hear a lot about from protein crystallographers. But the good thing about doing X-ray absorption is it actually gives us a good way to assess changes in the electronic structure. It's a very sensitive probe of radiation damage. So this is something useful if you're a protein crystallographer to actually be able to look at. And it's a good way to assess changes that might be occurring as a function of radiation. Probably most of you are more familiar with XFs than with Zane's analysis. One reason to be quite interested in Zane's spectroscopy is that it actually requires a lot less data collection time. These are generally easier data to obtain. You can typically obtain these data on samples that are much less concentrated than what you need to do a standard XFs measurement. In principle, if you have a sample that has multiple absorbers in it, say you're interested in the photosystem that contains both manganese and calcium, you can, in principle, do these measurements at both of those edges and get complementary information. And of course, all of these information you get from Zane's fundamentally complements other spectroscopic methods, be it synchrotron or non-synchrotron based. And so this is sort of, I think, hopefully a general theme that you get out of this workshop is this idea that if you can come at things from different perspectives with multiple approaches, you fundamentally will get a deeper understanding of the metalloenzyme chemistry that you're interested in. Okay, so let's talk about just a little bit about what this experiment looks like. I think an X-ray absorption experiment in many ways is conceptually one of the easiest experiments you can think about because most of us are fundamentally quite familiar with doing just regular absorption in a laboratory. And that's basically what this experiment is, but instead of absorbing optical light, we're now absorbing X-rays. Okay? And so this is just a schematic of a pretty standard hard X-ray beamline for a synchrotron measurement. This one happens to be beamline 9.3 at Stanford, which I know many of at least the PSU gang are quite familiar with. And so what happens in this measurement is you basically have an X-ray beam that's coming from the bottom right-hand side of this picture. You have a gas-filled ionization chamber that first measures the incident beam flux. Then you have a sample. In this case, it's sitting in a liquid helium cryostat. The beam passes through the sample and then is measured in an ionization chamber behind the sample. So if you're measuring in this configuration in a straightforward absorption measurement, you can see this is, in principle, very straightforward. We'll talk a little bit later about the fact that we don't typically measure actual absorption. So in that sense, even calling it X-ray absorption is a little bit of a misnomer, but we'll get to that later. We often might measure indirectly, say in fluorescence, and this is just an example of a fluorescence detector. Now, one of the things I want to point out is that this is an experiment that basically is designed for doing high-energy X-ray absorption measurements. So by high energy, I mean greater than 5,000 electron volts. Okay, so remember, it's roughly a little over 8,000 electron volts, or 8,000 wave numbers per electron volt. So this is a relatively high energy measurement. The nice thing is that this can all be set up in air, because at these high energies, the electrons have a very long path length. This is something to consider as you think about doing measurements at lower energies. In the 2 to 5 keV region, electrons have a relatively short path length in air. So a lot of times these become experiments that are done in helium. And at less than 2 electron volts for very low energy measurements, one often needs to be in vacuum. And so these obviously become challenges for biological systems, and it's the reason why in bioinorganic chemistry, most of the applications you'll see are in higher energy ranges. It's also for this reason that I'm going to focus primarily on metal K-edges that use these higher energy electrons. Okay, let's just look at the beamline in a little bit more detail before we get to more specifics of what we can get out of this experiment. So as I already mentioned at the start of my talk, in general, we're using a synchrotron source to provide this high-energy source of X-rays. Each beamline will typically have an insertion device. So this is either wiggler or undulator magnets that basically provide an enhancement of the intensity of the electrons. And then we basically have a series of optics before the experimental hutch that help us focus the beam, a monochromator that's used for energy selection. So this would be using Bragg's law to actually change the angle and select the energy. And then another mirror to focus before it actually comes into the user hutch. But in many ways, this monochromator is similar to an optical grating in an absorption experiment. One just has to think about all of these things a little bit differently, typically at synchrotron facilities, because of the high intensities. So for instance, this monochromator, which is a double crystal monochromator, at many synchrotron facilities, these are actually cooled by liquid nitrogen, and that's because the heat load is so high on the optics that you actually would start to distort it. So it's also a concern to keep in mind when you think about what could be happening to your samples. And this is just another view of one of the upstream X-ray mirrors that's used to focus it. But basically then, just in a schematic, just to make the experiment look a little bit more simple, what you fundamentally need is an X-ray source, some sort of monochromator to do energy selection, ionization chambers to measure intensities before and after your sample. If you choose to measure in a secondary way, you would need some sort of fluorescence detector. And if you're running at high enough energies, you could put in another ionization chamber with a reference sample, and then basically have a way to have a constant energy reference. And this is the way a typical high-energy X-ray absorption experiment is done. So one of the things I already said is that we typically don't actually directly measure the absorption. Not that we don't want to, but it's really pretty much only feasible for solid samples. So if you have model reference samples, you can actually measure direct absorption or transmittance of the beam through your sample. But if your sample is more dilute, which is generally going to be the case with most protein samples, you'll typically measure a secondary effect. So after ionization of the 1s electron, when that 2p electron, for instance, refills that core hole and produces a fluorescent photon, we might instead measure the fluorescence and make the assumption that the total fluorescence is proportional to the absorption. We'll talk more about these assumptions later, but this is just to give you a general idea of how we do this experiment. In principle, one can also measure electron yield. This, though, is not typically done for high-energy experiments, simply because the electrons have a very short path length in air, and the yields at high energies for electron yield are quite low. So there are actually reasons why at higher energy it's more advantageous to measure the fluorescent photons. But the good news about this is that, especially when we run with high-energy X-rays, we can measure samples that are solids, liquids, frozen solutions. Less relevant to the bioinorganic community, of course, is running gas phase samples, but you can, in fact, also do gas treatments of your samples in situ. And in general, one can, these days, go to pretty small volumes and relatively low concentrations. This will depend a bit on the beamline you're running at, the setup, But I would say that 1 millimolar is sort of the typical concentration one needs in an absorber. But data have been collected, for instance, at zinc as low as 50 micromolar. So it's possible, but it gets more challenging. So in principle, for many biochemists, we do often require relatively high concentrations, and it does depend on the protein that you're actually looking at. Okay, so that just gives you a very brief idea of the experiment. I don't want to go into that today in too much detail, and I want to spend most of the time looking together with you at data and talking about the kind of information that we can get out of these data. And as I said, because we're focusing on what's most applicable to bioinorganic systems, I'm going to focus for the purposes of this talk on metal K edges, where we're looking at 1s excitations. And in this case, I already kind of mentioned that this sharp discontinuity corresponds to the X-ray absorption edge. When we think about this in terms of simple selection rules, what this transition is, in principle, on iron is a bound state transition that corresponds to an iron 1s to 4p transition that I'm showing here in red. And so this, of course, has a delta L of 1, and that makes this a dipole-allowed transition. What you see if you zoom in, superimposed on this rising edge and blown up here so you can see it a little bit more clearly, is a very weak pre-edge. This corresponds to an iron 1s to 3d. So now this is formally a delta L of 2. It's dipole forbidden, but quadrupole allowed. That makes this transition, in principle, about 2 orders of magnitude weaker than the intense edge transitions. And this is, for instance, if one wants to get information about chemical bonding and what's happening in the D manifold, makes this experiment a little bit more challenging. But we'll talk about how changes in this region can also be very helpful and insightful. So let's just take a look at all of the factors that could affect an edge and just look at each one of these in more detail. So in principle, edges are going to be dependent on the oxidation state of your absorber, on the coordination number of your absorber, on how covalent the site is, as well as what the site symmetry is. And so what I'd like to do now is take just each of these examples and go through them one by one. And in principle, when we go through these, we can kind of have different mindsets in terms of how we interpret it. And there are many different ways that people interpret edges in the literature. Probably the most prominent way is to look at these edges in a qualitative way and to basically use the edges as a fingerprint of electronic structure, compare the edges to known models, maybe use principal component analysis to figure out what makes this up. And this is a very useful approach, but it's also a very qualitative approach. If one wants to get a little bit more quantitative, we can use a more molecular orbital-based approach where we're thinking from MO-based pictures. In this way, we can obtain a more quantitative picture that allows us to understand the energy and intensity distributions using a more ligand field-based model like we discussed this morning. And one way to do this is to couple it to density functional calculations, for instance, using time-dependent DFT approaches as are implemented in ORCA. And this is something that examples of which will be shown in the ORCA tutorial. The other way to look at this is in a multiple scattering-based approach using programs like FEF. We will talk about this more in the X-ray tutorial because this is really used for analysis of XFs. However, my preference in terms of talking about edges is to use more of a chemically intuitive MO-based approach. But in all of this, ultimately our goal is to, of course, understand and hopefully eventually predict spectra in a way where we can really extract more information from our experimental data. So let's just take a look at some very simple edges. So what I'm showing here in blue is copper 1, and in red, a typical copper 2 edge. And so here what you can see is the very simple effect of what happens when we increase the oxidation state on a transition metal absorber. What happens, of course, is that as the effective charge increases, it becomes harder to remove that 1s core electron, and it takes more energy. And so what we see experimentally is a shift of, in this case, several electron volts on going from copper 1 to copper 2. Okay? And of course, the same thing holds regardless of the absorber that we look at. So if we look at, for instance, iron-sulfur complexes, as we go from iron 2 to iron 3, we see this characteristic increase in the edge energy. Now, I actually also plotted an example of ferro and ferricyanide to show you, again, in this example, you do see a systematic change on going from iron 2 to iron 3. But the point I wanted to make by plotting these spectra is that you can see that the iron-sulfur complexes look entirely different than the iron hexacyanides. And this is something to be very aware of when you're trying to make comparisons in a very qualitative way using X-ray absorption spectroscopy, because you really need to compare oxidation state trends within similar ligand environments. Because you can see, of course, if we compare the iron sulfurs to the iron cyanides, these things look nothing at all alike. Okay? This is also the other reason that we would like to be able to better calculate these spectra in order to get more information out of them. Okay, so let's take a look at the effect of coordination number. Now, in this case, this is also work from Ed Solomon's lab, but because it actually happened in the late 80s, I can say it's ancient. But anyway, what basically they looked at in this study was the effect of coordination number on the rising edge. And what you can see here is as we go from 2 to 3 to 4 coordinate, these are all copper 1 complexes, but there's a big change in this 1s to 4p rising edge transition. And this actually can be understood using a relatively simple ligand field-based model. So if we think about just starting with an isolated copper atom, where before we have any ligands present, the 4p, xyz are all degenerate, then for our 2-coordinate complex, what I'm going to do is first bring in 2 ligands along the pz, raising this in energy, so I have a doubly degenerate pxy, lowest in energy. So now my lowest energy transition is to the doubly degenerate pxy. So now if I bring in another ligand, so now this becomes 3-coordinate with my ligands in the yz plane, I raise the energy of the yz, and my lowest energy transition will be to the 4px, and it should have roughly half the intensity of the 4pxy, and this is exactly what I see. And finally, if I go to a tetrahedral-like site, then the 4p, x, y, and z are all raised in energy, and this feature should effectively be gone. And this is exactly what happens. So this is a nice example of how one can understand something like coordination number trends in relatively simple qualitative pictures. Now, it's not always the case that it's so simple. So superimposed on these rising edges, these typically aren't clean 1s to 4p transitions, but there's the possibility that other things can happen after we create this 1s core hole. And so this feature on the rising edge, particularly in many copper 2 complexes, has been assigned as a 1s to 4p plus ligand to metal charge transfer transition. The basic model goes something like this. If we start here at our ground state, where we have a 3D 9 system, we look into the edge where we've now done a 1s to 4p excitation. And the idea is now that we have a 1s core hole on the metal, that basically the 3D then can relax below the 3p levels, making it energetically favorable to have a ligand to metal charge transfer. And this is referred to as a shakedown transition in X-ray spectroscopy. But the intensity of the shakedown can be related to site covalency. And so what one often sees, as sites are more covalent, this shakedown transition becomes more intense and lower in energy. And one can often use relatively simple, in this case, a simple VBCI type model to try to model what these effects are. But again, it's a relatively qualitative interpretation, but it can kind of give you an idea if you're comparing similar sets of models. And in this case, the similar sets of models are actually blue-copper proteins, where one is just doing a single point mutation and looking at the effect of that on the edge. Okay? But again, this is sort of to just drive home this point that one always needs to be careful and think about what it is that you're actually comparing. And so what I'm showing in this slide are examples of iron edges where all the irons are iron 3, But the differences you see are the differences between fluoride coordination, chloride coordination, and bromide coordination. And so in the absence of any information about what these complexes are, you might mistakenly say that the oxidation state has greatly changed. But there's clearly a lot more happening here. It likely matters just how ionic or covalent the ligand is. So it may be that these are actually these same kinds of ligand to metal charge transfer shakedown transitions that are superimposed. It could be differences also in the scattering properties or some combination of both. And so this is just why, in general, I sort of encourage people to exercise caution and have a pretty good idea from other methods what it is that you're comparing. And later we'll talk about ways that computations can also help sort out some of these types of trends. So let's look at the pre-edge in a little bit more detail and talk a little bit historically about where the assignment of these very weak 1s to 3D features actually comes from. This was something that was first sorted out by Schulman's group at Yale in the late 1970s. And the nice experiment that they did was to look at a series of transition metal hexafluoride complexes. And they basically made the observation that if they had manganese, iron, cobalt, nickel, they always had a pre-edge transition. And it was only that when they went to zinc that they noticed that this weak transition was absent. And so they were really the first people to indicate that this, in fact, could be a 1s to 3D quadruple allowed transition, but in fact that it also could be due to vibronic mixing of 3D and 4P levels. This was something that was then later sorted out by Ed Solomon's group, looking at polarized copper K edges of D4H copper tetrachloride. And this is a very nice experiment. So inherently, synchrotrons allow for polarized measurements. So if you have a single crystal, you can actually look as you rotate around this phi axis. You can see what happens to, in this case, the intensity of the pre-edge. And in this case, what they saw was an interesting fourfold periodicity in the intensity of the pre-edge that was consistent with a quadruple contribution. What they also saw, however, was a constant offset in these data. So that indicates some spherically symmetric contribution consistent with some small amount of dipole. That could come from vibronic coupling. It could come from a misalignment of the cell, the crystals within the unit cell. But this experiment made it very clear that this was, in fact, a true 1s to 3D quadruple allowed transition. And what's kind of interesting about this is that one can go back to your undergraduate group theory and really get a very intuitive understanding of these kinds of spectra. And so this is a very nice example of just looking at how symmetry changes the intensity of these pre-edges. So as I said, these are 1s to 3D transitions. In principle, they are only quadruple allowed and should be very weak. And if we look at something like ferric hexachloride in an octahedral coordination environment, that's exactly what we see. We see just a very weak pre-edge. Now here, if we think about this, this is really a pure quadruple-based transition. Here, by group theory, the 3D orbitals are of the wrong symmetry to mix with the 4p orbitals, right? You already heard this morning, of course, that in octahedral symmetry, our 3D orbitals transform as T2g and EG. Our 4p orbitals transform as T1u. And so there's no possibility to gain intensity through this mechanism. But what happens instead, if we go to a tetrahedral, now our 4p orbitals transform as T2, and our d orbitals also, the dxy, xz, and yz, also transform as T2. And as a result of this allowed mixing, we basically gain dipole allowed character, and the pre-edge becomes very intense. And what's nice about this is this means that the pre-edge can be used to actually get some information about what's happening to the local site symmetry of your absorber, and what's happening to, for instance, the coordination number. So basically, as a result of this, there are certain established paradigms in the analysis of metal K-edges. And so this is actually based on work that was originally done by Larry Kay's group, and then a more detailed follow-up study by Ed Solomon's group, where they basically showed if you looked at wide series of iron complexes, the 6-coordinate complexes always had much lower intensities than the 5-coordinate complexes. And so just like we did on the previous slide with octahedral and tetrahedral, you could go back to your character tables and pretty quickly figure out why this is the case. But this has now been used quite a bit in bioinorganic chemistry to determine what the coordination number is around an active site, just by comparing to known models. There are also sort of other established paradigms that are also based on simple ligand field-based models, and that is this general idea that if we compare things in similar coordination environments, as we increase oxidation states, so in this case going from iron 4 to 5 to 6, we see about a 1 electron volt increase in the pre-edge energy, and this reflects both the increase in Z effective as well as the increase in ligand field. Now, I think one thing that maybe is also a theme in my talk is this idea that we can understand these simple models, but we also have to be aware of the fact that there are going to be exceptions to these rules, and then we want to do our best to actually understand those exceptions. And so what I'm showing here now are those same data for 6-coordinate and 5-coordinate iron complexes, and I'm comparing it to an iron model where we also are 6-coordinate, but now we have a chelating nitrate that basically distorts the local geometry. And although this is a 6-coordinate complex, you can see it has an intensity that's actually more similar to a 5-coordinate complex. And so in a case like this, if we use just a simple fingerprint, we might arrive at an incorrect conclusion about what the coordination environment of this site is. However, in this case, it's a small molecule. We had a crystal structure, and we can actually understand that this comes through distortions, and that those distortions give us a loud p-mixing, which increases the intensity. Okay. Similarly, the sort of idea that we can just read oxidation state from a comparison can also be misleading. Here I'm showing an example where we compare iron 4 to an iron 5 complex, and in fact, they're at exactly the same energy. And so one might say the oxidation state assignment is wrong, but when one looks at the structures, you can actually understand that the difference is that the 4-coordinate complex, or the iron 4 complex, is 6-coordinate, whereas the iron 5 complex is actually 5-coordinate. And so it's actually, again, a difference in ligand field that can also affect these shifts. And that's why it's very important to understand all of the components that actually go into our observables. And so this has been something that my group and I, over the last, I guess, 8 or 9 years now, have been really interested in sort of doing, is basically asking to what extent we can go beyond these relatively qualitative interpretations and really use theoretical approaches to better understand our data. And so this is something that we've been doing in collaboration with Frank Nazo's group and using the ORCA program to actually do. And this is a very nice example of the kind of agreement you can get by using time-dependent density functional theory to actually calculate these kinds of edges. And so here I'm going back to the same example of using, looking at octahedral versus tetrahedral ferric iron. And what you see, we can include both dipole and quadrupole contributions in these calculations. For the ferric hexachloride, you see that there's only quadrupole contributions, so just this blue feature, and the dipole is absent, just as we would predict from group theory. And when we go to the tetrahedral complex, of course, we still should have some quadrupole contributions, but then most of the intensity gain should come from dipole. And that's exactly what we see, and we can generally get these intensities and trends correct. And so we, in the time since, have been interested in asking, can you extend this to wide ranges of compounds and make sure that you can always predict the changes based on a given structure? And here, I'm just showing a range of high-valent iron complexes. And although these are all high-valent complexes, you can definitely see there are differences in the energy and intensity distribution. And in general, this is very well reproduced by these kinds of approaches. And so this is kind of the path towards making these types of calculations more predictive. And so one of the things that one does when you do these kinds of comparisons is to sort of look at the correlations between experimental and calculated areas, and to sort of define that over a wide range of compounds, these correlations remain linear, both for the areas, but also for the predicted energies. And that's what you generally see. So if you were to apply these kinds of methods to another transition metal, what one would want to do is to establish this kind of correlation set. Okay, but that's just sort of, I guess, a brief advertisement for the kinds of things you can do with time-dependent density functional theory in the edges. And now what I'd like to do is switch gears a little bit and move to the information that we can get out of the extended X-ray absorption fine structure. And so I already gave you a very simple picture of this, but basically in the edge region, I think it's a place where chemists feel a bit more comfortable because we can think in molecular orbital-based pictures. We can think about transitions into bound states. But now, when we think about XF, we're now thinking of this as a photoelectron wave vector, basically. And it's a wave that's propagating out from our photoabsorber. And at some point, it interacts with a neighboring atom, and it is backscattered. And that backscattering, when it returns at the absorber, can be interfering with the outgoing wave in a constructive way, which will give you a maximum in your signal, or it could be interfering in a destructive way, which will give you a minimum in your signal. But of course, this is a simple picture of just an absorber and one scatterer. And the reality is we have many more scatterers in any molecule. And so we minimally have to think of what's referred to as multiple scattering. And that's the idea that this photoelectron is scattered by more than one atom before it returns to the absorber. The ultimate goal with fitting XFs is to try to deconvolute all of this information and to understand what all the possible scattering pathways actually were. And for those of you who do the tutorial, you'll see it quickly can become quite a complex problem. Nonetheless, there are certain things that with XFs we can do really quite well, and often much better than protein crystallography, and that is to get distance information local to the absorber. So typical estimates on the errors for XF distances are on the order of plus or minus 0.01 to 0.02 angstroms. Now, it's important to remember that X-ray absorption and XFs are a little bit plagued by the fact that we always see the average of all photoabsorbers. So we see if we have two different iron sites, we'll not be able to separate them out. We see the average of those two iron sites. But that said, we get the average distance quite accurately. What you do see, though, is that coordination numbers have a larger error, so typically plus or minus 20 to 25%. We can identify types of ligands. So a larger ligand, like a sulfur, will scatter very differently than a lighter atom, like a nitrogen. However, carbon, nitrogen, and oxygen are all light atoms, and by scattering-based methods, they all look the same. So as a general rule, types of ligands we can tell within Z plus or minus 1, typically. We can get out some near-neighbor information, but XF dies out as 1 over r squared, so typically we can't go beyond 6 angstroms beyond the active site. So it's a very local method. And we can get bond angle information in certain cases. Okay. So let's just take a little bit of a look at how one actually goes about actually extracting the XFs data, and this is also something we'll be doing in the X-ray tutorial. But as I already said, when we look at X-ray absorption data, we're looking at the changes in the absorption coefficient mu as a function of energy. So we have this very intense edge that's very easy to see, but just looking at these data so far, you don't see anything that looks like XFs, and that's because we actually need to extract the very weak fine structure from the post edge. We do that by first subtracting a pre-edge to remove any of the lower energy processes or scatter. And then the next thing we do is actually to remove a spline. The idea with a spline is that we're actually trying to remove the atomic background. When we do XS, Of course, this photoelectron wave vector can actually scatter off the atomic potential of the absorbing atom. But we're not interested in that information. That's going to be information that occurs at very short distance and very low frequency. So the idea of a spline is actually to model that atomic background or the absorption due to the photoabsorber without any neighboring atoms. Okay? So in principle, this is an experiment one could only correctly do in gas phase. But when you do that, what happens then is you get something that looks like this. This is the actual EXAF signal. And now quite a few things have changed about it. We're no longer in energy space. When you look at EXAFs in most publications, you're actually in K space, which has units of reciprocal angstroms. Okay? Now, in order to get to K space, the way we do that is we actually have to define a point E0 in energy space. This point E0 in energy space is the start of your EXAFs, the K equals 0 point, or the point at which that photoelectron has been ejected to the continuum and can interact with its neighbors. Not surprisingly, E0 is something we have to fit because we don't actually really know what this value explicitly is, and you'll see that it can change the way the EXAFs actually look. Typically, though, because the EXAFs oscillations are so weak and they die off at higher energies, you'll typically see data are weighted by K cubed, and this is just to enhance these oscillations so we can actually better see the sine wave that makes up all these interactions. The goal of actually fitting the data is to deconvolute this resultant sine wave into all the individual paths that make it up. You can also better visualize that sometimes by taking it from K space, which is in reciprocal angstroms, and transforming it into R space in angstroms. So this is now a Fourier transform of our EXAFs, and the way to think about this is if this is the absorbing atom here at point 0, then basically this Fourier transform means that around 2 angstroms, there's a whole lot of stuff backscattering. Okay? So this would indicate I have some ligands at about 2 angstroms. Be careful, you can't read the distance directly off a Fourier transform, just like protein crystallographers or anyone doing any scattering-based method. We also have a problem with knowing what our phase shift is. As a rough rule of thumb, you can add about 0.3 to 0.4 angstroms off of what you see experimentally, and you'll have a good guess of your starting distance. Okay? So let's just look at this in a slightly more mathematical form. So as I said, what we measure at the beamline is this mu e, the modulation of the absorption coefficient as a function of energy. When we remove the spline, that is now the atomic portion. This is our mu 0 that we're actually subtracting from our data and then normalizing by a simplified version of the spline. Okay? So this gives me my chi of E, or my EXAFs in energy space. I then do the transformation into K space, and basically then get the expression that you've already seen. Now, the idea here is that if I want to get chi of K into something that actually looks more like sine waves, then we basically just model this by scattering. And so the idea is that we have an outgoing photoelectron, and we have the returning photoelectron. And what we need to do is basically modulate that photoelectron wave due to the fact that it interacted with a backscatterer. And whatever that backscatterer is, it will have certain amplitude parameters, and it will have certain phase parameters. And so if I have a really big backscatterer, like a copper, that will modulate differently than a small backscatterer like an oxygen. Okay? But basically, the idea with this is to get something that looks a little bit more like the EXAFs equation. What we need to do is basically just multiply out these exponentials and re-express this as a sine function. And so this sine function will then have a linear dependence on n. This is the coordination number, or the number of given backscatterers. And because it's modulated by both the outgoing and the returning wave, it will end up having a 1 over r squared dependence. This is what makes EXAFs a relatively local method, because it dies off as 1 over r squared. Now, right now, this expression doesn't allow for any disorder in our system. Sorry, my laser pointer keeps. It doesn't allow for any disorder in our system, and we actually add disorder in terms of this exponential, where this sigma squared term of the exponential is the mean square disorder in a given distance. And this is what in XS is often referred to as the Debye-Waller value. Okay? But this is basically the way we go about basically using this relatively simplified equation. We can basically model and figure out what the distance and coordination number is, provided that we have input for both the phase and the amplitude parameter. Okay? And so, yeah, I don't have enough hands is the problem. Okay, that's fine. Thanks. Okay. And so this is now just basically what we already went through, but I've just now redefined all of these variables. And I should point out in the XS literature, you'll see the amplitude function expressed as A for amplitude, but also as f of k. And I noticed, I apologize, I used both in my slides as well. And the phase function is either delta or small alpha. Both of those appear in the literature. Okay? But I think that for those of you who are less mathematically inclined, this is also a very easy effect to see visually in terms of how does each change in the x-axis actually affect my signal. And so here, what I've done is to just do simple x-axis calculations for different possible bond lengths. And so what you can see here is I have a copper nitrogen at 2 angstroms, 3 angstroms, and 4 angstroms. And so what you basically see is as I increase the distance, this becomes higher and higher frequency. You also see that the amplitude decreases. So what you're really seeing here is this 1 over r squared dependence. And you can also very nicely see this in the Fourier transform as the signal just dies out as we go further. Okay? The other thing that's perhaps very straightforward to think about is to look at how coordination number actually affects your x-axis. So this is now completely linear. This is just looking at 1 copper-nitrogen interaction at 2 angstroms versus 2 versus 3. You can see the linear increase in your amplitude of your x-axis signal, and similarly a linear increase in the amplitude of your Fourier transform. And so these are relatively easy things to at least start to get some comparative intuition about when you look at different data sets. Okay. So perhaps the most dramatic effect is the effect of what the backscatter is. And as I already mentioned, a light atom like oxygen versus a heavier atom like copper will have very different amplitude and phase modulation. And so I've calculated a copper-copper at 2.5 angstroms versus a copper-oxygen at 2.5 angstroms. And you can see that it has a much stronger amplitude. It's in part because, of course, copper has more electrons. It's a much stronger backscatter. And this is very clearly reflected in the Fourier transform, which has much more intensity. So this means that one of the things XS often does very well is to identify the presence of metal-metal interactions. So for multi-metallic sites, this is quite helpful. Okay. So the other thing that I should talk about is the effect of the Debye-Waller factor on the XS signal. So as I already said, the Debye-Waller is basically a disorder in the bond. And so in general, we tend to think that this primarily represents static disorder, because at least for most biological systems, measurements for XS tend to be done at 10 Kelvin. This means the thermal contributions are effectively removed, and we're pretty much looking at static disorders, so different distributions of distances, or perhaps, remember, because we see the averages, the average contributions, it might reflect 2 ligands at slightly different distances. So say one at 1.95 and one at 2.0. That would give me a larger Debye-Waller than having 2 ligands exactly at 1.95 angstroms. Okay? And so this is just an example of a change in Debye-Waller of about a factor of 5. And so again, one sees the effect on the amplitude in the XS and in the Fourier transform. I already mentioned that the Debye-Waller is obviously going to have both thermal and static components. And this is now just comparing what happens to XS if we're at 10 Kelvin versus being at room temperature. And so you can also see this argues strongly for doing measurements at low temperature if you can. because basically the structure doesn't die out nearly as quickly. And once we add a thermal component, you can see our signal dies out quite quickly. It also makes it much harder for us to model the X-AS, because then we also now have to separately model static and thermal components. And so this sort of speaks strongly not just for the reasons of radiation damage that I mentioned earlier, but also for obtaining more detailed structural information. It's often useful to be at lower temperatures. Okay, so the other point that I should bring up is this effect of resolution. As I already said, X-AS in general, although we can get very good precision on our average bond distance, we're not very good at separating out similar backscatterers. So if I have two histidines, one at 1.9 angstrom and one at 2 angstroms, what I'm going to do is just see the average at 1.95. In general, the resolution of X-AS data goes as delta R, so the resolution in angstroms, as pi over 2 delta K. This means to get 0.1 angstrom resolution from my X-AS data, I need to get data to nearly K of 20. And so this is a real challenge. And for anyone who's ever done any X-AS and metalloproteins, they'll probably tell you not so easy to do. So most of the time, when we're dealing with data to K of 13 or 15, we're talking about resolutions of 0.15 to 0.1 angstrom for similar backscatterers. And that is a limitation of the method. Now, you can actually visualize that if you look at what happens to data as we increase K-space. Now, this is data complements of Graham George. I think he's one of the few people who has managed to get data out to K of 21. This is molybdenum X-AS data on a molybdenum dimer that has dinitrogen bound between the two molybdenum sites. So right now, you see K-space out to about K of 9 and the corresponding Fourier transform. And if we look at what happens as we go further and further out, you can see that there's this great sharpening effect, and we also get more structural information. So although these data tend to be very challenging to get, they can considerably enhance the sort of structural information you might be able to extract from your X-AS data. And so let's just briefly summarize the kind of information you get from X-AS. So the frequency of your X-AS gives you distance information. The phase shift of your X-AS tells you something about the type of the atom. But our biggest problem are the amplitudes, because the amplitudes tell us something about the type of atom, but they also tell us something about the coordination number, and they also tell us something about structural disorder. So what you can see right away is that there are some inherent problems with highly correlated parameters in X-AS analysis. And so this is why, in general, one can rely on distances, but some of the other parameters really need backup, I think, from other methods oftentimes. So let's just take a brief look at sort of just breakdowns of components. This is just for you to understand this a little bit more detail. I already mentioned this idea of multiple scattering. And what I'm showing here are the paths that would result from iron with bound cyanide. And here you can see the data in FIT, which looks quite nice. And you can see below it all the components that make it up. These components include two-body interactions, so an iron to carbon and backscattering, or an iron out to the distant nitrogen and backscattering, as well as three-leg paths, where the wave is scattered by the carbon, the nitrogen, and goes straight back to the iron, or four-body paths, where we go through each atom, both on the outward and the inward direction. Now, obviously, if we know what the unit is, we can link these parameters and reduce the variables. So that's something else that's helpful. But this just gives you an idea of what this kind of looks like. So the thing about the multiple scattering that's also very useful, even though it looks a little bit complicated, is that it inherently can provide us with some angular information. And so what I'm showing here is what happens to the multiple scattering as I actually change this iron-carbon-nitrogen angle. This is obviously hypothetical. But what you can see is at 180 degrees, I have a very intense peak that comes both from the scattering from the near carbon as well as from the far nitrogen. Both of these are very intense. As I start to change this angle, the intensity of this outer feature starts to fall off, and it doesn't start to increase again until I get closer to 90 degrees where this nitrogen effectively becomes a second bond. Okay? The idea with excess multiple scattering is there can be a strong forward focusing effect of that scattered wave vector. And so when we're near 180 degrees, the multiple scattering will give you very intense outer shell features. But as we deviate from 180 degrees, that effect will decrease. And this means that inherently one can also extract some angular information in these models, which can be quite useful. Okay? And so sort of to be a little bit more biologically relevant, one can also imagine these same sort of paths in a histidine. And so here I'm just showing you what the various possible scattering paths look like in a histidine. And you can quickly imagine that this gets quite complex. But what we can also tell is information about the actual orientation of the histidine. So as we sort of change this in or out of plane, we actually should get different outer shell multiple scattering, and that can give us some orientation information about the histidine. But again, this is relatively challenging. Okay. So in the interest of time, I'm actually just going to skip ahead here a few slides and just briefly comment on how XS data are fit. This is something that we'll go through more in the tutorial, but the general idea with trying to fit XS and not being overwhelmed by all these possible different multiple scattering paths is to basically start by building an initial model. So this is a place where calculations can help you a lot. If you don't actually have a crystal structure, you can build and optimize a model. Use that to actually calculate your initial distance and disorder parameters, optimize those parameters relative to your experimental data, and then basically go back and reevaluate through this process until one arrives at a structure that's in agreement with experiment. And this is the process that we'll be going through starting on Sunday at the tutorials. One of the things I wanted to point out, though, is that although I showed you we're at a point, I think, where we can get quite a bit of real predictive information from at least the pre-edge region using time-dependent DFT approaches, this is unfortunately less the case with XS. And so one has to be careful, at least in my view at this point in time, XS data still require fitting. And so what I'm showing here are data in black on a manganese dimer and the various predictions using FEF. These are basically using different approaches within FEF. But what you see is the data are shown here in black, and particularly in this outer shell. Even though this is a small molecule crystal structure where we know exactly what it is, none of these data agree terribly well with the outer shell. And so there really are cases where even though we know the small molecule structure, we have to be careful about using XS in a predictive way. Now, it's not to say that it never works. Here's a nicer example. This time I chose a monomer where we don't have significant multiple scattering. And here you can see that regardless of the level of theory I choose within the FEF program, that I generally always have pretty good agreement. And so this is just something that one has to be aware of, but the sort of current state of the art still requires some sort of fitting. Okay, so let's now in the last part of my talk, I'd like to switch gears a little bit from X-ray absorption and talk a little bit about what we can do if we instead collect X-ray emission at moderately high resolution. Now, I already told you early on that when we do these experiments, if we have dilute samples, we typically measure in fluorescence mode. And so that basically means we would use something like a solid state detector. Typically for high energies, those are germanium detectors. And what we would do is with that detector, we would electronically window, for instance, in iron on the K-alpha line that corresponds to the 2p to 1s and the fluorescence that results. And we would basically just electronically window here. And as we scan the monochromator through our edge energy, we would assume that all of these fluorescent events are proportional to our total absorption. Okay, that's the way we normally do this experiment. And now the question kind of is, what other information can we get out if we can start to think about measuring these emission spectra at higher resolution? And so typically solid-state detectors have an E over delta E of about 40. This means that iron, their resolution is about 175 electron volts. And that means that these emission spectra have effectively no fine structure. And so one way to actually start to get fine structure on the emission spectra is to actually measure at higher resolution. And so it's effectively a very similar experiment to any X-ray absorption experiment, but instead it becomes a two-bounce experiment where you use the optics to obtain higher resolution. So here, if you imagine this is the incident beam coming in, here is the sample. The sample now is fluorescing, and instead of going straight to my detector, it instead goes to a spherical optic that spectrally analyzes that fluorescence and reflects it back onto the detector. And so now, instead of having an E delta E of about 40, I can improve that to about 5,000, or more than 2 orders of magnitude. And so one can really start to get very high-resolution emission spectra. And the question to ask is then, what kind of information can I get out of these spectra? Okay? And so let's just look at this first graphically. So again, this is just a very simplified energy level diagram now for, say, an iron. And what we're going to do is we're going to come in with a high-energy source of X-rays, and we ionize the 1s electron to the continuum. And now, instead of following absorption, we're just going to follow the emission processes, which means we're going to look at what happens when the 2p electron refills the 1s core hole and produces fluorescence. This fluorescence is the K-alpha fluorescence. Historically, that's the nomenclature that's used. It's going to be dominated by 2p spin orbit when that 2p core hole is actually produced. And it's probably chemically not the most interesting, so I won't really be talking about this today. I will point out, though, for those of you who are generally interested in doing X-ray absorption, K-alpha detection enables higher resolution detection, and I will talk about that in my talk at the symposium next week. But for now, we won't really focus on this other than just to, in passing, mention that K-alpha detection can give you higher resolution. The other possibility is that a 3p electron refills the 1s core hole. This is about an order of magnitude less likely, so the K-beta lines will be weaker. But they're actually dominated by a 3p 3d exchange interaction. And what this means is once I create that 3p core hole, I now have the possibility of interaction between that p hole and my unpaired d electrons. And this means that K-beta lines can actually be used with certain caveats as a marker of a metal's spin state. And so you can get also, by detecting off the K-beta main lines, to some extent, you can get oxidation state and spin state dependent X-ray absorption. And so in some sense, if you combine the high resolution detection that I'm talking about with a traditional X-ray absorption experiment, you basically further the information you can get out of it. Okay, and then the least likely possibility is that a valence electron refills that 1s core hole. These are very weak, several orders of magnitude weaker than the K-alpha lines, but they are highly sensitive to ligand environment because, of course, they're coming from ligand valence orbitals. This means the valence to core emission can give you a measure of ligand identity, ionization potential, protonation states, and it also enables possibilities of ligand selective X-ray absorption. So what I would like to do is just sort of briefly go through some of these spectra so you have sort of an idea of what they look like and the kinds of things that one could get out of them. And so what I'd like to start with is just by covering work that we did now about 4 years ago, looking at just really simple iron model complexes. This is a series of ferric complexes at the K-beta mainline. And so here you can see the spin state effects that I was talking about. This is ferric tetrachloride, ferric ACAC, and a ferric porphyrin with an axial chloride. And at least from a relatively zoomed out perspective, these are all superimposable. They have this shoulder distinctly here and a more intense higher energy feature. When we go to low spin complexes like ferric hexacyanide, ferric TACN, or ferric TPP bisamidazole, you can see this feature is gone. And now the overall shape is quite different. And so these, in principle, can be used as markers for spin state. Chris Pollack has done recent work that show that this can be complicated by effects of covalency. if you guys just want a fun activity later over a beer, you can work out the multiplets for these spectra. I'd be happy to help you because I think it's fun, but we won't go through that right now. What I'd like to focus on right now is this valence emission region. And what we see here is that although these main lines are all pretty superimposable for these complexes, you can quite quickly see that as we change the ligation environment from 4 chlorides to 6 oxygens to the 4 nitrogens of the porphyrin and a chloride, there are dramatic changes. Okay? Similarly, the low-spin complexes all have very unique spectra, and there are, in fact, even differences in intensity between these spectra, whether you have a high-spin or a low-spin iron site. And so there is clearly a lot of information here about the chemical environment and information that can, in principle, be quite complementary to XAS. Similarly, one can also look at ferric complexes, and again, you can see the trends. Again, the high-spin complexes having a distinct shoulder that's referred to as a K-beta prime, and that becomes absent in the corresponding low-spin complexes. Okay? And so overall, if we just look at this a little bit more numerically, what we see, just like we saw for the X-ray absorption edges, we see that the emission also shows oxidation state dependent shifts in energy, but there'll also be contributions of spin state. And one of the interesting effects here is also in the valence emission, where you see there's a factor of 2 to 3 difference between high spin and low spin complexes. And we'll talk a little bit later about the origin of that. But basically, what we did was we really wanted to, again, see to what extent that we could use theory to understand these spectra. Because this is, in many ways, I should point out that X-ray emission spectra are by no means a new method. This is something that physicists have known about for decades and decades. But it hasn't really sort of come to the chemical community. And so I think a lot of what my group and I have been doing is just asking the question, what is the chemical information content of these spectra? And this is where DFT approaches have been incredibly helpful. So as you can see, yes, we're ORCA fans. And the approach that we are using is, as Frank generally puts it, a criminally simple one-electron DFT approach. But the good news is that it works. So we're basically looking at, always have to tamper theorists with real experiments. So, but it's basically, we're just looking at the energy difference between the one-electron cone sham orbitals. We're using the very simple requirement that there needs to be metal character in the molecular orbital that's involved in the emission process, and that intensity is governed simply by a dipole operator. So it means if my ligand orbital has some metal p character in it, I get allowed emission intensity. And so I won't go through these correlations. We'll just look first instead at the data. But what you can see here are early experiment and theory correlations for the ferric high spin and low spin complexes. And what we found was these are largely all dipole. They're 97% dipole contributions that actually make up these spectra. So again, it's just a small amount of ligand P, a small amount of metal P mixed into the ligand orbitals that gives you this allowed intensity. And similarly, what you can see for the ferric complexes when you compare experiment and theory is that we, again, get very good agreement between experiment and theory. Now, one of the things I want to point out is that although it's not generally the case, but in this iron series, what we see is that unlike the iron K edges, symmetry doesn't make a major contribution to the valence emission, because now we're actually looking at P character mixed into the ligand orbitals as opposed to directly probing the metal 3D. And so what we see here, if you look at the blue and the red spectra here by experiment, this is the difference between tetrahedral ferrous tetrachloride and octahedral ferrous hexachloride. They're basically near superimposable by experiment and also near superimposable by theory. And just as a reminder, this contrasts what we saw at the K edge, right? And it makes sense because we're actually probing something different. But I think it sort of highlights the complementarity of these methods. And so that's just a useful thing to keep in mind, that you can get different but complementary information if you look both at the X-ray absorption pre-edge as well as these transitions from the filled ligand orbital into the metal core hole that in principle together should all agree with the same electronic structure, one hopes. Okay. And so when we actually look at these calculations in more detail and ask what's actually making them up, what you can see is these features to higher energy. This is the so-called K-beta 2,5. Physicists name these so that they make no sense to us as chemists, but they basically correspond to, in this case, chlorine p orbitals, and to lower energy with less intensity, a transition that comes primarily from a chlorine 3s in this case. Now, as soon as we go to more complex ligands, this quickly becomes more complicated, but just in a simple picture, you can dominantly think of higher energy as ligand P, and lower energy is ligand S. Okay? Now, what I want to comment on is this dramatic change in intensity that one sees between high-spin and low-spin complexes. It actually turns out to derive from a relatively simple picture. There's basically an exponential decrease in intensity as one actually increases the length of the metal-ligand bond. Okay? So it's not a direct correlation with spin state. It's an indirect correlation with spin state. And just low-spin complexes, of course, tend to have shorter metal-ligand bonds. You therefore more effectively mix metal P character into the ligands, and the intensity increases. And that's what we see. But it does mean that, sort of complementary to excess, there's inherently the possibility of having some structural information in ligand emission. And probably one of the nicest things about it is that it can tell you something about the ligand ionization potential. And so we talked about the fact that for excess, carbon, nitrogen, and oxygen all look the same. They're light atoms. They all scatter in the same way. But now we're actually looking effectively at the ionization potential of the ligand. And what we see then, in this case, particularly here in the ligand 2s-derived features, that there are very large shifts going from fluorine to oxygen to nitrogen. So this is almost, I think, 8 electron volts over this span. So it's pretty dramatic shifts when you think about that in wave numbers. And it means that this can be very useful for distinguishing different ligand types that can be coordinated. Similarly, it can also give you some indirect information about the ligand hybridization that will perturb the spectra, but in a very subtle way. It can also give you some information about protonation states. So this is now just a hypothetical calculation where we've looked at what would happen for a protonated or unprotonated ferryl species in compound 2. And what you see is this very big effect, which reflects the shift in the 2s ionization potential upon protonation. Okay? And this has been applied by Vera Kraywald to real complexes, where she's looked at manganese complexes with 2 oxos, an oxo and a hydroxo, and 2 hydroxos. And what you see are these very clear shifts that allow you to actually distinguish. And this, in principle, then can be very helpful when you're trying to distinguish different intermediate species. Okay, so just in the last part, what I want to just briefly highlight is some of Chris Pollock's work from his thesis that really sort of was the work that kind of detailed what the contribution of the nature of the ligand is to these spectra. And so one of the things that we noticed early on was that there are really big differences in these spectra depending on if you have a sigma-only donor like TACN, a sigma donor pi donor like ACAC, versus a sigma donor pi acceptor like a cyanide. You can see that these features are very different. And so at first we kind of liked the idea that maybe we could also have some sort of measure of pi backbonding, and this was something that, that Chris looked at in detail to really sort of examine what's happening to these spectra from the perspective of the ligand. And this is kind of a useful way to have a more intuitive picture of what these features are one's looking at. And so to do that, what he did was to actually look at the difference between the metal emissions, so now this will all be localized on the iron, versus the ligand, ligand-based emission. And so now the ligand-based emission, of course, is just a theoretical construct. It will be very intense because it's all dipole allowed. But what you basically see is that, that if you look at a simple ammonia and you predict what the ligand emission would look like for this, you're basically going to see a feature that corresponds to each of the filled ligand-based MOs. Okay? And so this is kind of a good way to have a simple conceptual picture of it. If you can think about what the MO diagram looks like, you can start to think about how the ligand emission should change. And so then what Chris did was to actually then take the simplified single ammonia, arrange them in space, look at the effect of a point charge versus the effect of adding a metal. And what he basically sees is that the effect of adding a metal isn't so different than the effect of just adding a 3+ point charge. We basically just get primarily stabilization of the lone pair on the ammonia. So that's the major spectral modification that occurs. And if you compare now this calculated ligand emission to the calculated iron emission, what you see is that this dominant peak actually comes from the lone pair of the ammonia. So this really explains why you have just a single feature for a sigma-only donor. Okay? And you can do the same thing with, for instance, a cyanide. And there, what you can actually see, again, you can construct your very simple MO picture, but now you have two intense features, one that comes from the sigma 2p, and the other that comes from the sigma star 2s antibonding interaction. So in fact, we don't see any significant contributions from the pi-type orbitals. They actually have the wrong symmetry for mixing. But it means that we can understand these features. And what Chris has since shown is you can also use this to look at bond activation. So for instance, he's shown how you can see the activation of an N2 bond by looking at these changes in energetics. But sort of kind of the summary picture of this is that if you can go back to your undergraduate course and sort of reconstruct things like diagrams for ferrocene, when you get to something even more complex like a CP ligand, really all of these predicted features where the 2s now splits into A2U and E1U combos, and similarly the splittings of the 2p, they really predict a feature in the emission. And so it really is a picture that in general is quite simple and then can be relatively straightforward in terms of calculating. The nice thing about this, too, is that you can effectively, once you know what a ligand contribution looks like, even before it interacts with the metal, you can start deconvoluting these spectra into their sort of component parts. This is something that Mario Delgado in our group has done a lot of work on, but basically to sort of map out what the contribution of a carbonyl is. In this case, this is a low-valent iron, so you actually see the occupied 3Ds contributing to the spectra. If we go from iron pentacarbonyl to iron with 3 carbonyls and a COD ligand, we can see that the CO feature stays the same, but decreases in intensity because there are fewer COs. We have a clear signature for COD and also a signature for the 3D. So basically, each light atom type will have a unique signature based on its ionization potential. And these are the kinds of things that you can start to map out and extract from the emission. So just the general sort of take-home message from this is, of course, that X-ray absorption, of course, probes unoccupied. I'm in trouble for that. It says states, but anyway. I've become a physicist. Whereas X-ray emission is going to probe your filled levels. And together, what these give us is really a sort of detailed picture of the electronic structure that, in principle, one should be able to map back on to a molecular orbital picture. Now, in the last part of my talk, I had some applications, but I think in the interest of time, I'm not going to go through these. You can feel free to look through them on your own. And I guess before I finish, I'd just like to encourage questions maybe before the coffee break if anyone has any. So thank you.
Thanks, Serena. There is a question.
Thanks.
What kind of concentration do you need to look at the K-beta edge?
I'm sorry, what kind of what?
Concentration do you need for?
Oh, to do a K-beta edge detection? I mean, in principle, I guess the question would be what metal also? But I would say for iron, I mean, for the K-beta mainline, you should be able to get it from 1 millimolar. For valence emission, it's a challenge, and in general, I would tell people at least several millimolar because it's so concentration challenged. Yeah. Yeah.
What is the physical meaning of the frequency of each component in the K-phase?
Oh, the physical meaning of the frequency is the distance. Okay, so basically, the longer the distance, the higher the frequency. And so when we remove the spline and sort of model the atomic contributions, that's very low frequency that has to do with very short distance scattering. Okay. Yeah.
Well, I actually do a lot of XFs, but something I've always kind of thought about, and I always ask my boss over and over, and he tries to explain it to me, but I'm interested in a different perspective, is when we're looking at the XFs, what phenomena are we actually looking at? When we have the white line, right, somebody decided, what's going on as we go out past that into the XFs? Is the are the electrons coming back from the continuum? You know what I mean? Like, do you see what I'm asking?
No, I mean, so basically, yeah, I mean, I think this is often the case for chemists that inherently we don't have a picture of the XFs that we like. But it really has to be that the photoelectron has already been ejected. And so you do have, in principle, you're no longer dealing with sort of a simple picture of bound states. You have an ionized 1s core species, and now as a function of energy. Exactly. So you are, I mean, yeah. So basically, at every energy, when the wave returns to the absorber, that modulation is different at every single energy. Yeah.
Talk briefly about photoreduction.
Yeah.
What, at least for XFs, what kind of load of energy will your sample be giving that you can be sure that it's not also being photoreduced?
Yeah, no, that's an excellent question. So I think one wants to be very careful about using sort of rule of thumb metrics. There are many in the literature that have since proven to be wrong. So the problem is it's highly, highly system dependent. And if we could only predict how sensitive each and every system we run is to photoreduction before the experiment, this would be great. But we can't do that. So in general, one has to do careful dose-dependent studies every single time you do it. And you basically can hopefully do things like attenuate beam and filter beam until you reach a point where you no longer see any time-dependent damage. But that's about all you can do. And for certain systems, like the photosystem, it's incredibly challenging. For other systems, like nitrogenase, it's incredibly stable. So there are big differences. Other questions?
Other questions? Well, then let's thank Serena again. So we have our coffee break, and we will reconvene at 4 o'clock. Les Dutton has arrived. And if you have problems with the wireless, Lorraine and Stacy are in the lobby, and we'll try to help you. Okay?